Hello everyone, Sahil here. Today we will learn about k-means. It is by far the most widely used clustering algorithm and this will be really interesting for you as well. So let's just start. So before getting into the nitty-gritty of k-means, let's have a brief introduction. What is k-means? K-means is an unsupervised learning algorithm. So unlike KNN, which is a supervised learning algorithm, in k-means we don't have any labels. We only have the features, but we don't have any labels assigned to our data. K-means is used for clustering, which is a form of unsupervised learning. Unsupervised learning can be divided into clustering, association, and dimensionality reduction. So supervised learning can be divided into regression and classification, and unsupervised learning can be divided into clustering, association, and dimensionality reduction. And k-means is one of the most popular clustering algorithms. So what is clustering? What do we mean by that? Clustering is basically finding patterns in our data. We are trying to organize our data. We are trying to discover these different regions in our data. So basically, k-means is also used for astronomical data analysis. And a good analogy to understand k-means will be we have this universe and we are trying to find different galaxies. So there are these different planets, these different particles which are clogged up together in a specific region and which we call a galaxy. And this is one cluster. Galaxy is basically a cluster. So k-means basically does that. It tries to find these different clusters in our data. And when we talk about the learning process of k-means, we basically see that it learns through iterations. That's why it is called an iterative algorithm. So when we will learn about the learning process, how k-means exactly discovers these different regions, these different patterns, these different clusters in our data, we will know why we will call it an iterative algorithm. Now to understand the concept behind k-means, the logic behind k-means, the various steps we take, the procedure and the reasons behind them. Why do we take those steps? What is the intuition behind that? So let's look at it this way. You have your data, you have your training points, maybe thousands or in tens of thousands training points, and you don't have any labels assigned to them because it is an unsupervised learning problem. And when you have these training points, so I have illustrated them as bees. So you can see there are five beehives here. So in this case, you already know where your clusters are. You have five clusters here. Now let's say you don't know. You don't know where your clusters are and you want to discover them. Now, what we do in k-means is that you take some queen bees. Now, you take those queen bees in your hand and you just throw them out. Now, these different clusters, they stay there. They are your training examples. And the queen bees, they move. They have the choice. The queen bees, they will go to different clusters and it will try to figure which clusters belongs to me, which cluster is mine. So the queen has the choice. The training example, the normal bees who belong to these clusters, they don't have the choice. They will just see which bee is nearer to them. So let's say if we have two bees and the first bee is nearer to a specific cluster, then that cluster of bees will accept, okay, this is our queen. Now these bees in these clusters, they are your training examples. And the queen bee which is moving around and trying to figure out which cluster is mine, they are your centroids. They are the centroids of the clusters. Now in k-means, there are two steps. The first is the cluster assignment step and the second is the move centroid step. So the procedure I just explained you here, it is exactly what we do in k-means. So the cluster assignment step is the first step. In cluster assignment step, basically the bees see which queen bee is nearer to them, and then they declare them their queen. That is the cluster assignment step. And the move centroid step, which is the second step, that is the step where the queen decides, okay, which cluster actually belongs to me and where should I go. So let's see and let's look at these steps in more detail now. So, as I explained you the intuition behind k-means with the example of bees and queen bees, let's see them more in a mathematical way now. So, the first step is where we randomly initialize case cluster centroids. We randomly take k number of queen bees and we just throw them out. And then we repeat these two steps. The first step, the cluster assignment step, and the move centroid step. We repeat these two steps until we reach a certain conclusion. Until the bees, the queen bees, have decided that these are our cluster and they stop moving when they are sure. And this is the iteration that goes on until we reach a certain conclusion. That's why k-means is called an iterative algorithm, because we are taking iterations. We are iterating until we reach a certain conclusion. And one iteration consists of these two steps, the cluster assignment step and the move centroid steps. So let's look at these two steps in more detail now, in a more mathematical way now. So now we are getting into the details of our algorithm. So what is our input? What is the input for k-means algorithm? What does it need? So the first is k. K is the number of clusters. It is a hyperparameter that you have to learn. And the second is our training set. And notice that there are no labels there because it is an unsupervised learning problem. We only have the X, we only have the features, we don't have the Y, we don't have the labels. Now let's understand the cluster assignment step. We already have the intuition behind it. So what do we do here? In the cluster assignment step, we basically assign clusters. We assign cluster to training examples. Every training example gets assigned a specific cluster. Which cluster? The cluster which is the nearest to it. So let's say that we have m training examples. So we will have m numbers assigned to those training examples, and these numbers will be the cluster. It will be the cluster number. So let's say that we have m training examples and we have k cluster centroids, and we run a loop over the training examples. And in the first iteration of this loop, I is equals to 1, that is the first training example. What we will do inside this loop is that we will measure the distance between the first training example and the k cluster centroids. And let's say that we measure the distances and the minimum one is the fifth one. That is, the distance between the first training example and the fifth cluster centroid is the minimum when it comes to the distance between the first training example and the other cluster centroid. That is, the fifth one is the nearest one. So for the first training example, I is equals to 1. The cluster centroid assigned to it is the fifth one, that is the k is equals to 5. Now we have to store it somewhere and we store it in C. C is an array same as the length of the training set. For every training example, we have to store the number, we have to store the cluster number for every training example, and we store it in C. And this loop runs for all the training examples. So basically, in a nutshell, what we are doing is that for every training example, we are just assigning the clusters which are nearest to those training examples. This is what we do in this loop, and this is the cluster assignment step. Now the second step is the move centroid step. Now this is the second step, and as I told you earlier that this is the step where the queen bees basically move and they make a decision based on the fact that which cluster seems to be theirs. Now what I didn't tell you is that how do they make this decision. Now they make this decision based on the fact that which training examples think that I am their queen bee. So the queen bee basically sees, okay, which training examples are voting for me. So the array that we stored in the cluster assignment step, the queen bee basically sees that, and it sees, okay, that the first training example thought that the fifth cluster centroid is his cluster centroid. Now, if I was the fifth cluster centroid, I was the fifth bee, what I would do is that I would go near to that training example. So this is what we do in this. So you can see the loop for every cluster centroid. We do some operation inside that. What do we do here? So let's say that for the first cluster centroid, what we do here is that we go through that array, we go through that CI array where it is written, okay, this training example thinks that this cluster centroid is what it belongs to. Now what it will do is that you have to understand this, that every centroid, every cluster centroid has a coordinate. It has a position in the feature space, and it is the same as any training example. So let's say that each training example is three dimensional, that we have three features. So every cluster centroid will also have a coordinate x, y, z. It is something like that. It will have a coordinate, it will have a position in that three-dimensional space. Now what it will do is that it will take the training example which thinks that this is the cluster centroid which is nearest to us, and it will take the average of them. So for every cluster centroid, it will take all the training examples which think that he is their cluster centroid, and it will take the average of their coordinates and move itself to that position in the feature space. Now to repeat it again, let's say that I am the cluster centroid and I see in the array, in the CI array, and I see that there are 10 training examples which think that I am their cluster centroid. So what I will do is that I will take those 10 training examples and I will take their average, I will take their mean. Basically what I'm trying to do is that I am trying to go near them because I think that they are the cluster that I belong to, or I this is my cluster. And this is how the bees take their decision. They see the bees which think that okay, this is our queen bee. This is the basis on which the centroid moves. So this is the move centroid step, because in this step basically every centroid accounts for the training example that think that okay, this is our centroid, and every centroid take those training example and takes the average of them and move itself to that position in the feature space. Which position? Which is the average of the training points, which basically thought okay, this is our cluster centroid in the first place. This is what we do in the move centroid step, and you can see that the loop starts from 1 to k because there are k cluster centroids, and we do it for every cluster centroid. Now you might be thinking that where is our optimization objective, because unlike knn we have a learning process here. KNN was a brainless algorithm. It doesn't learn. That's why we didn't have a cost function in the first place. But we know now that k means actually learns. But where is the cost function that we have to minimize? We actually do have a cost function here. And it is a bit subtle actually, because it is not expressed in our training. But we are actually minimizing that in the two steps that we did. So let me explain that now. In those two steps, the cluster assignment step and the move centroid step, if you see a pattern, if you try to understand that what we are doing there, we are basically trying to minimize the distance between the training example and their respective cluster centroid. So let's say that I am a B, I am a training example, and I have a specific cluster centroid assigned to me. So in those two steps, the cluster assignment step and the move centroid step, we are basically trying to minimize this distance, and we keep on doing that until we cannot do it anymore. So the cost function that we have here is that we have the training example and we have its specific cluster. So we have the ith training example, and for the ith training example we have a specific cluster assigned to it. So which cluster is that? That cluster number is C of I. So the cluster which is assigned to ith training example will be new of Ci, and we are basically trying to minimize that distance. Now we are not using this cost function specifically to minimize it and find the weights. So what is the use of it? It is really useful actually, because you can use it to do the hyperparameter tuning part. Because when you will be using different hyperparameters, you need some kind of number, you need something to tell the difference between two different set of hyperparameters to know which one is the better one. Now, before we get into that, let me explain you how this cost function is actually being implemented in those two steps. So in the cluster assignment step, you can see that we are assigning the clusters, but the clusters themselves, the centroids, they are fixed. So we are only learning, we are only minimizing this cost function with respect to the C's. We are only minimizing the cost function with respect to the Ci of that part, C1 to Cm. But in the move centroid step, we are minimizing this cost function with respect to the cluster centroids because we are changing the news. So basically what we have done is that we have partitioned this cost function into two steps, but it is the same cost function. We are minimizing the same thing, which is the distance between the training example and its respective cluster centroid. And we keep on doing it until we cannot do it anymore. So we started from the introduction and we understood the intuition behind k-means. I also told you the different steps we take in k-means, what is the logic behind those steps. After that, I explained you the optimization objective, what is the logic behind that, how can we use that. So now we are ready to implement our algorithm. So there are many different ways to implement k-means. You can use different libraries, different frameworks, but to really understand k-means, I would highly recommend that you implement it from scratch in Python yourself first. Because when you are learning something, you think that you understand something, but when you will implement it yourself, you will understand a lot of things and you will discover a lot of things that you thought you understood, but no, you haven't understood those things. So to really grasp the thing, you should implement it yourself. So after that you have tried it, let me just explain the implementation. So the first step is that we import the necessary libraries. So we import numpy as np. So as np means that I will use it with the name np. So what is numpy library? Numpy library is used for mathematical operations, specifically for matrix calculations. Because in machine learning we do a lot of matrix calculations, numpy really helps us with that. The second library is the pandas library. Now what is the pandas library? It is basically the standard for tabular data. So when you have tabular data, you have lots of tables, rows, columns, and you have the CSV files, you want to process them. You use pandas. It's used everywhere and you should really know how we can use it. It is really essential for machine learning practitioners. So the second step is that we connect with our Google Drive. Now, why are we doing that? So I downloaded the dataset that I will discuss later and I uploaded it on my Google Drive. So to access my dataset, I have to connect with my Google Drive. So we have imported the necessary libraries that we want to use and we are connecting with Google Drive to access our dataset. Let us just do the next steps now. Now that we have connected with the Google Drive, let us just access our dataset. So you will see I have written this code here, pd.readcsv, and I have written some path. So what does it mean? So the read CSV method, so first of all, PD is the pandas library and we have a read CSV method here. CSV basically means comma separated value and a CSV file is basically like an Excel file. So you have these tables, these rows and columns and you have written different values in there. So to express that file, we use a CSV file. To read that CSV file, we use the read CSV method. And when we use this method, it basically reads the CSV file and converts it into a data frame. And the data frame and the CSV file, they are not that different. It's just that it is a better representation. And when it comes to machine learning, you have to do different operations on that table basically, and data frames just works better. So that df basically means data frame. The second line, I have written df.columns.values and it's pretty self-explanatory. I am asking for the column values and you can see different values here. It starts with the customer ID, then balance frequency, purchases. So these are different features that we have. And in the third line, I have dropped the customer ID column. So df.drop basically means to drop that column. And I have written 1 there because it means the first axis. The first axis basically denotes columns. So why did I drop that column? I dropped that column because the customer's ID doesn't really mean anything. It doesn't really express something about the customer. It is just a number. There are different features here like the balance frequency, the purchases. They do represent the customer's behavior, their different patterns, their habits, but the customer's ID doesn't really add anything. It basically adds hindrance because it just confuses the algorithm. That's why I just removed that column. So you can see that I have called the command df.head. It basically tells us to just show us the head of the data frame because it is a really big table, it is a really long table. So just show us the data frame in a shorter way so that we can just check that everything is all right. So after removing that customer ID column because it wasn't really helpful in the training process, in the learning process, the next step we will do is that we will do feature scaling. So what is feature scaling basically? Feature scaling is that we will take every example, and so we will take each and every example and we will subtract the mean of every feature from that example, and we will divide that with the standard deviation of every feature of that example, every feature of the data set basically, and we will divide that example. So basically what we are doing is that, so let's say that we have three features, 1 2 and 3, and we have like 100 examples. So for the first feature we have 100 numbers, so we will take mean of those 100 numbers, and this is the mean of the first feature. And so similarly we will take the mean of the second feature and the third feature. Now we have these three means, this is the mean vector. Similarly, we will get the standard deviation vector. It will be also a three-dimensional vector. So when we get any example, we will just subtract the mean out of that and we will just divide it by the standard deviation. So why do we do that? So when we are training, when we are learning, we have these contours, we have these learning curves. And when there is a huge gap, there is a huge difference between different features, this contour, propagating through this contour, propagating through this learning curve, it becomes really difficult. It takes more time, it takes more effort. But when you basically do the feature scaling, your contours, your learning process, it becomes, the contours become more circular if we are talking in two dimensions. But basically it makes the learning process more smoother. And you might think that in k-means why do we need this? So we can say that if we have some feature which has a huge magnitude, but how will it impact our algorithm? So when we have another feature which has lower magnitudes, it is basically a bit of partiality. It is basically a bit of bias from our side because the algorithm doesn't know. It is the same example. The algorithm doesn't know the difference between three bedrooms and like 400 square feet. 400 square feet is more than three bedrooms for the algorithm because it doesn't understand the concept between the two features. So that's why we do the feature scaling. And you can compare the same data frame that I showed you earlier, and you can see that now the values are between -1 and +1, and they are more spread apart, they are evenly spread apart because I subtracted the mean out of that. So this is basically a step which makes the learning process better for you, and I recommend that you do this. So if you look at the code, how am I doing that? First of all, I get n, which is the df.shape of 1. So basically I am getting the number of columns. So if I had done df dot shape 0, I would have gotten the number of examples. So it is the height. So if df dot shape 0, it is the height. It is the number of examples. And df dot shape 1, it is basically the number of columns. It is the width. So I get the number of columns and I iterate through each and every column. So as I told you earlier that we had these three features and we have 100 examples. So for the first feature we have 100 values. Now we will just sum up these 100 values and divide by 100. That is the mean. So that is what we do here. We go through each column. What does the column mean? The column means one feature. So the first column will be the balance column. You can see here in the table below. This is the first column. So we are getting that column using df.ilog, and we are using that symbol and I. It basically means that we are getting the ith column. So we get the ith column, and for the first iteration it will be I is equals to 0. So it is the first column, it is the balance column. So the values that you were shown in the previous slide, it will get those values. And as I told you earlier that NumPy, which we are using as NP, it helps us in mathematical operations. So we use the np.mean to get the mean of all the values from that column, and we also use the np.std to get the standard deviation. So that's what I told you earlier. We just abstract the mean and divide it by the standard deviation, and we just replace that column with this new column. This new column has the mean subtracted and it is divided by the standard deviation, and we do it for each and every column. This is feature scaling. So now we have accessed our dataset and we have pre-processed our dataset as well using feature scaling. Now we have to do the algorithmic part. Now we have to do the mathematical part. So as you would remember, the first step was to just initialize k random cluster centroids. So one thing I need to tell you here is that we just don't randomly initialize numbers out of the blue. We initialize the numbers in a specific way. So let me just tell you how we do that. So you have these data points scattered in the feature space. So how will you just randomly initialize some data points that you will call your random cluster centroids? So you will not just initialize any point. What you will do is that you will get random indexes of your own data set. So you have your training examples and you get k random instances from your training examples, k random indexes, and you access those data points. You access those data points, and these are your k random cluster centroids. So I have written the function for that because you have to repeat it again and again. You will call this function afterwards. So what do we do here? So this is the initialize clusters function and you give k. You tell it how many clusters you actually want. So it just gets the number of examples in a data set. So df.shape0, it is basically the height. It is basically the number of training example. It gets that in M. And now we just tell it to just sample some unique numbers between 0 and M, basically between 0 and m minus 1. So we just want k random numbers which are integers and which are not the same. They are unique numbers, they are different, and they're in the range 0 and m minus 1. So we get those indexes and we get these random indexes, and what we basically do is that we get the indexes, and using these indexes we access those instances in our training set. We access those random data points from our training set and we just add them to a list, and that is what we return. So this list named mu, basically it just has the randomly initialized clusters, the news, because we represent the mean as new. That's why I named it as mu. So the second thing that we have to do, which is the first step, this is the cluster assignment step. So as I told you earlier, what do we do in the cluster assignment step? We basically assign clusters. To whom? We basically assign clusters to every single training example. We go to every single training example and we ask him which is the nearest cluster centroid that you can see. And he says, okay, I think that this one is the nearest to me. Then we say, okay, this is cluster number I, and this is your cluster number. This is what we do in this method. And of course, to compare with those randomly initialized cluster centroids, we need those cluster centroids. That's why you give it the input, that is the mu. You give all the cluster centroids and you start with initializing a list named C. This will basically just collect all the cluster numbers of all the training examples. So let's say the first training example is closest to second cluster centroid. So C of 0, because the first index is 0. So C of 0 will be 2 because it is the second cluster centroid. And you get the number of training examples and you go through every single training example. You get that training example x is equals to df.i log I. So you access the row. This is how you access the row in a data frame, and this is your first example, I is equals to 0. You access that training example and you create a new list named diff. It will basically collect the distances between this training example and all the clusters. So in the next step, in the next loop, which is for j in range 0 of to length of mu, you basically go through every single cluster centroid and you collect the distance and you just save it in this list. And what do you give it to the C, the list named C? You give it the index which had the minimum of the difference, which had the minimum distance. The minimum distance is the nearest cluster centroid, and you give it the index of the nearest cluster centroid for the ith example. This is one iteration, and you do it for every single training example. You are basically asking every single training example which is the nearest cluster centroid that you can see, and he says, okay, this is the cluster centroid I can see, and we give the index. Remember this, you don't give the example yet, you just give the index of that cluster centroid. So if you have k cluster centroid, you will have 0, 1, 2, 3 till k minus 1. These are the numbers that you give. So this is how you do this. This is the cluster assignment step. I have written a function here because k-means is an iterative algorithm. You have to repeat it again and again. So you will just call this function rather than writing the code again and again. So after the cluster assignment step, after the fact that every training example has decided which is the nearest cluster centroid, what is the next step? The next step is the move centroid step. Now is the turn of the centroids to act. And what do? The centroids just go to the center of the training examples, which basically welcome them, which basically accept them. The honeybee will just see which are the bees that actually accept me, and I will just go to the center of them. I will just go to the average of them. So if 10 training examples accept a particular cluster centroid, it will just go to the average of that. And that is what we do in this move centroids function. So we create a new list mu, and you might say that we already have a mu list. Why are you creating a new list with the same name? I am creating a new list because the MUs that we had before, they will change. Why? Because they will move and they will have new coordinates now. And that's what we will calculate in this function, and then we will return the new MU list. So what do we do after that? In the cluster assignment step, we went to every training example. So it went from 0 to m minus 1. Now we will go to every cluster centroid. This is the turn of the centroids. So we will go to k cluster centroids, that is 0 to k minus 1, and we have that loop here. And in that loop, the first line is indices I for I x in enumerate C if x is equals to j. What does it mean? This is a list comprehension, and basically what we are telling it here is that for the value of x in C, so every value in C, if it is equal to j, then give me the index of that. So basically, if j is equals to 0, that is the first cluster centroid. If in the array C, if in the list C, we have the value 0, give me the index. So basically, just give me the address of the training example, which is basically accepting me. So we get all the indices here, we get all the instances, we get all the addresses of the instances, because we have the indexes of the training examples. And now what we will do is that we will go through each and every index, we will go through each and every index, and we will get that index and we will just sum it up. And what we will do after that, we will just take the average of that. So this is really simple. Just ask every training example which is the nearest centroid, which is the cluster assignment step. And now we every centroid will just see which is the training example that actually accepted me. Just give me that training example. It accesses that, it takes the average of them, and it just changes its position, and we have the new mu list, we have the new centroids. So these new positions of centroids, now that our previous centroids have moved to these positions, and because k means is an iterative algorithm, we will repeat it again and again. That's why I have written it in a function. The last part is the cost function. And I told you earlier that cost function we will use for basically debugging the algorithm to make sure that we have coded it right, that we are doing the right things, we haven't made any mistake. Our cost function basically signals us for that. It gives us the right direction. So what is the cost function? The cost function is basically trying to minimize the distance of every training example with its nearest cluster centroids. So that's what I have coded here. The cost is basically the distance of every single training example with its cluster centroid. So we go through every single training example, that is 0 to m minus 1, and we get that training example. Now this training example, what is the cluster centroid of this training example? Now try to think about it. Let's say that the first training example 0 told that the second cluster is the nearest to me. Now what did we save? We saved the index. So we have that information, and that index was saved in C. And for the zeroth example, the zeroth index of C basically gave us the cluster number. So we can get the cluster number of ith example from C of I. And when we have the cluster number, we can basically get the cluster by just giving that cluster number to the mu list, which has all the clusters. And that's what we do here. We get the training example, the ith training example, which is df.iloci. We get the ith row and we get its cluster, and we get the difference of that, and we just put it in the formula, which is the square divided by the number of training example, and that is what we return. This is the cost function. This is what we have to minimize. So we started from the data set, we accessed the data set, then we pre-processed the data set using feature scaling, then we did the coding part. So we initialized the clusters and we then coded the two steps, that is the cluster assignment step and the move centroid step, and we also coded our cost function. Now everything is set and we need to start our training. Now I also told you in the brief introduction of k-means that k-means is an iterative algorithm. Why is it called that? Because of the learning process. And now you will see that because the learning process is basically iterating. We are basically doing iterations. So let me just explain you that. However, you already know this. So this is the coding part. So first of all, you initialize the hyperparameters. So you initialize the number of clusters, which is k, and we have decided 5 for now. You will get the best number of clusters using the elbow method and the trial and error method, as I told you earlier. Now the second is the number of iterations. The number of iterations is basically how many times do we want to iterate this loop. How many times do we want to do iterations, because sometimes you have actually reached convergence, but if you keep on iterating, you are basically wasting resources. So if you have already reached convergence, you have to stop iterating because nothing is changing now. The centroids are fixed, they are not changing their positions. So we have initialized two lists as well, and this will help us in our plot, which I will explain you later. So we start with initializing our clusters. So we give it the k. So we have initialized our clusters, these randomly initialized cluster centroids, and we have it in the list named mu. And we just run the loop for number of iterations, which is 30. And what do we do in there? First of all, we do the cluster assignment step. We assign the clusters, and then we do the move centroid step. In the cluster assignment step, we just assign every training example the nearest cluster, and the indexes of those cluster we store it in the list named C. Now in the second step, which is the move centroid step, we basically give this information to the centroids themselves so that they can see which are the training examples that actually like them, that actually accept them. And then what do? They go to the average, they go to the center of those training examples which voted for them in the same place, and we just append this information in x and y. So in x, basically I am storing the iteration number, the number of iterations, and in y I am storing the cost. So we do this training part, and after that I plot it. So I have used the matplotlib library, and it is just really simple and you will use it a lot, so you should understand this. So I imported the matplotlib library as plt, the pyplot part, and I just plotted plt.plot x and y, and it just plots a graph for me, and I can get some information out of this graph. So you can see in this graph the number of iterations around 15 and 20, around somewhere in between 15 and 20, we can see that our algorithm has already converged. So after the like 16th or 17th iteration, we weren't learning anything. We had already converged because the cost is not really decreasing. You can see the cost actually started from 10.6, which is a really big number, and then it gets decreases and it keeps on decreasing. And you will see that it only decreased to 9.4. And the reason for that maybe we haven't chosen the right number of clusters. This is where you will do the hyperparameter tuning. And what will you do with that? You will just take different values and you will use the elbow method. And it is the same as I explained you in knn, k nearest neighbors. You will implement the elbow method and you will get the best value of k. So you have the best value of k, and you will use that value and you will get the best convergence, and that will be the best or the best representation of clusters in your data set. However, if you have a different objective, as I told you earlier, if you have a different objective, if you want to get 5 clusters, then you will use this obviously, because this is the best. If you want to get 5 clusters, this is the best you can get out of that. Because in supervised learning, there is no right answer. You decide what is the right answer because there are no labels to tell you what is the right answer. The right answer depends on your objective, your results, your motivation. Now that we have implemented k-means in Python from scratch, we understand each and everything, we understand the algorithm in depth, we can use different frameworks and libraries to make our task a bit easy. So I have shown you this sklearn implementation here, which makes your task really easy, and you can just implement k-means in like 5 lines of code. So let me just explain you what are the things that really matter here. So you just import the k-means object from the sklearn library. So you have this object and you initialize that. How do you initialize that? You give it some parameters, and there are some parameters here named n clusters, init, n init, max iter, toll. So these parameters, what do they mean? So n clusters is basically self-explanatory because cell n clusters is number of clusters, which is k. We chose k is equals to 5 previously. Here we chose k is equals to 3. Init is equals to random. Init is equals to random means initialize. Init means initialize your number of clusters, initialize your clusters randomly. Init is equals to random. The third is n init. How is it different? N init means number of times you initialize your algorithm and train. So you have defined it 10. It basically means that train your algorithm 10 times with different values of randomly initialized clusters. So we did it only once previously. We took one value of, we initialized once basically. We initialized the clusters once and we trained. This is saying initialize them 10 times and then train and get the best ones. Because maybe you initialized, maybe you got lucky or maybe you had bad luck, and because of that you didn't get the best results. So initialize them again and again and get the best value of the hyperparameters. Specifically k is the hyperparameter that really matters. The fourth is max iter. So this is the same that we did previously, which was 30 number of iterations. So this is the maximum number of iterations you have to run your algorithm for. So sometimes we have to define this value because otherwise we will just keep on running. So we have to define some threshold that you have to train till this number of iterations so that we can declare convergence. And how do we declare that convergence? First of all, we just define the number of maximum number of iterations, then we stop. But we can also declare convergence before that. We don't have to go through all the number of iterations and then declare convergence, which we do by toll. Toll basically means tolerance. So we defined our cost function value. How do we calculate our cost function? So let's say for the first iteration, for the ith iteration, there was certain value of cost function, and for the I plus 1th iteration, for the next iteration, there was another value of cost function, and we haven't exceeded the number of maximum iterations, we are still iterating. But the difference between the value of cost functions, these two cost functions, between these two iterations is really low. And if it is less than a certain threshold, we declare convergence because it's not decreasing a lot. And that difference, that threshold, that difference is the tolerance level which we have defined here. So if you haven't exceeded the number of maximum iterations, you can declare convergence beforehand if the cost function is not changing very much, which basically means that the centroids aren't moving anymore. So you have reached convergence. So you shouldn't just keep on iterating and waste your resources. So this basically does all the job that we did previously, all of the code. And you might think that this is really easy, but this is for the other part. This is to help you with the other part. The other part is the hyperparameter tuning part, because you will choose different hyperparameters, you will get different results, and you will compare them, and that's how you will get the best model. So to code that, you use these libraries to make your task easy so that you can focus on the other part, which is a bit more important, because you can implement the algorithm, but if you don't get the best results, what is the use of it? So you focus on the hyperparameter tuning part, get the best hyperparameters, and use these libraries, use this code to get the results, compare the cost function, compare what the results are, and get the best values of hyperparameters. That is what you have to do for your own objective, for your own motivation. It will depend on that. Now here comes the hyperparameter tuning part, and this part is really important because you understand the intuition, you understand the logic, you have understood the mathematics, and now you also know the implementation part. But this is the part which is the most important, because if you don't know this, you won't be able to get the results that you desire. So how do we avoid local optima? So now let me give some context here, because you have unsupervised learning here. You don't have any labels here. There are no right answers because you don't have any labels to tell you which is the right answer. So let me give you an example. So let's say we have three classes: humans, cats, and dogs. Okay, so we have these three classes. Now, because you already have an idea that in this data set we will have three classes, you set k is equals to 3 and you get the results you want. You get the good results. But let's say you don't know that and you set k is equals to 2. And because you have set k is equals to 2, the algorithm will find some different structure in the data that might not be what you are desiring. It might not be the structure that is beneficial for your results or your objectives. It might categorize cats and dogs as one class and humans as other class, just because of the fact that cats and dogs both have four legs and humans have two legs. But this structure is misleading. This cluster is misleading because cats and dogs are not the same thing. So it basically means that if you get the wrong value of k, you can get the wrong results. And the wrong results basically mean local optima only, because you are not getting the right optima. You are not getting the global optima, which is the right structure which give you the best results for your specific use case, for your specific objective. Now, what is the solution for this problem? So the solution here is that because in this algorithm you are randomly initializing the k cluster centroids and you are just throwing them out, it can happen that the cluster centroids that you have initialized, they get initialized in a position, because it is randomly initialized, they get initialized in a position that they get different clusters, and maybe those clusters are not the one you want. Now how do we counter this problem? Basically you do it again and again. You randomly initialize the k cluster centroids because that's the only option you have. You randomly initialize them and then you train, and then you do it again and again and again. And how do we compare these different results? You use the cost function, you use the optimization objective that I told you about earlier. You see the values you have there. You train it again and again for different values of k, and for different values of the randomly initialized k cluster centroids as well, and you see which one is giving you the lowest value of j. This is where the cost function becomes really important, because it helps you debug the algorithm. And because it is an unsupervised learning problem, you don't have any labels, you don't have anything that can give you an idea that the results you are getting are right, that you are in the right direction, and you are already randomly initializing the k cluster centroids. The cost function becomes really important, and it will help you pick the right values. Now, the second thing that is really important, which can actually make or break your algorithm, just like in KNN, it is the value of K. So, because there is no automatic way to do this, and to be honest, in an unsupervised learning problem, it is really ambiguous which is the right value of K. So, the solution, you have to use the elbow method with the trial and error method, same as you do in KNN, the same approach. This is what you can do to get the value of k. And other thing that is really important here is that sometimes there is no right value of k. You have to decide the value of k yourself. Now, what do I mean by that? Let's say that you have a certain objective, you have a data, and you want to find clusters according to your interests. There are no clusters which are right. You can find the clusters any way you want. You can have the same data, you can get 10 clusters, and you can use the same data to get 2 clusters. It depends what you want out of that. So let me give you an example. Let's say that you are a marketing company, and you want to know that how many sizes of shirts do we want. So let's say you have data of your customers, and you have three sizes: small, medium, and large. And you have these thousands of customers, and you have their sizes as well. And now you want to categorize them into small, medium, and large. Now, because there is no specific or right cluster here, the cluster is according to your interest and your objective. You want to divide it into small, medium, and large because that is the product you have, and you want to estimate how many small and how many medium and how many large shirts should we make to serve for these customers. So now you already have the value of k because it is according to your objective. The other thing that you can use here is that when you have some data, if you can do this, you should do it. You can already have an idea that this data will be categorized into this number of clusters. So you can do this, but it is basically a trial and error method only. You can try that value and see whether it works good or not. So let's talk about the applications of k-means at last. As I told you earlier that this is one of the most popular clustering algorithms, and you will really like it. It is really exciting and interesting. So the first one is market segmentation. I already discussed this. Let's say that you have an array of products, you have certain products, and you have data of your customers. Now you can create clusters out of the data to estimate every product's performance. And you can get a lot of information out of that, and you can increase your sales. You can basically do business analytics. You can analyze your business, and you can think about the ways you can improve and earn more money. The second one is social network analysis, and this is a really attractive one. So let's say that you have a social networking site. Now, because you are using that site, you can use the person who has the social networking site. He can use your data points. He can use the data points of all the people, and he can generate clusters out of that. And because of the things you do on that social networking site, the things you type, the things you search, the things you see, everything can be collated and data can be created out of that. And it can estimate a lot of information about you using that. And clustering is one of them where you get this information. So let's say that there are two political parties, and we have this specific social networking site. Now, this social networking site can actually use these data points to estimate two clusters out of that, and it can basically estimate the political opinion of the populace. And it is very interesting. It is really interesting and it really has a lot of information it can get. Really exciting stuff. The third one is organizing computer clusters. So we have these different call centers and they have a lot of computers working together. And to get the information out of those computers easily and to speed up the process, K-means is sometimes used. Clustering algorithms are sometimes used there to organize these clusters to get more value out of that. The fourth one is astronomical data analysis. So as I was explaining you about K means that you are trying to find structures, you are trying to find clusters out of the data. Astronomical data analysis, because it is so large, you cannot analyze each and every single point. You use these algorithms to cluster and get the information out of that. So this is how you can use K-means for these four applications, and you can also use it for a specific use case depending on what you want.